Hello, hello. 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 Hello, hello. Hello. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Let's continue our class where we will discussing uh, the continuation of chapter 3, focusing on the multimedia data part 2. As for the class outline, we will be covering the following key topics: the compression classification, history compression, lossless compression, lossy compression, and some examples of the common compression algorithm and codecs. We will begin by looking at the different ways compression can be classified. There are two main categories, which are the spatial compression, where we find the similarities in an image and compress those similarities in a smaller form using the intraframe techniques. As for the temporal compression, we find the similarities across images and frames, and we compress those using the interframe techniques. Okay, and we also will discuss the compression classification based on the quality, such as the lossless, where no information is lost, or the other one is lossy, where some information will be sacrificed to achieve a higher compression. As we know, the digital media, like images, video, and audio, are usually very large in raw files. Okay, and it will create a few key challenges. Like the first one, we we often wouldn't have enough storage. capacity to hold a large number of uncompressed data or uncompressed files. The file size quickly add up. Okay, and secondly, communicating with those large files across network would be painfully slow without some compression. And by transferring uncompressed video file over the internet also would tax the patience of even the most tolerant user. Okay, and finally, we don't want to sacrifice too much quality and fidelity of the media when compressing it. So, some loss of quality may be acceptable, but we would like to minimize it. So, this raises an important question. Is it possible to reduce the size of these large digital media files significantly without incurring a major loss of quality? And the good news is, yes, there are the compression algorithm that can reduce the file size dramatically while retaining the excellent quality. And we will exploring these techniques, both lossless and lossy, throughout this lecture. Okay. So the key is by applying the right compression methods, we can achieve a substantial file size reduction without noticeable reduction in the quality. And this will enable the efficient storage transmission of media files in your application. Right? So let's see the lossless and lossy techniques. Okay, when we discussing these two techniques, there is it is important to distinguish which one, what is the difference between the lossless and the lossy compression. Okay, the lossless compression, as the name itself, okay, it's compressed data in a way that still allow the original data to be reconstructed perfectly when decompressed, and no information is lost between the compression and decompression. Okay, some examples of lossless compression methods are the RLE, the run length encoding, and the Huffman coding. Okay, these reduce file size by identifying and eliminating the redundancy without discard any information. Okay, as for the contrast, a lossy compression algorithm accept some loss of information to achieve the higher compression ratio. Okay, when the data is decompressed, so it will not match to the original data anymore. But there are the key benefit of a lossy compression, where uh, the compression is much greater for multimedia data types. Okay, for example, we have JPEG, MPEG, and MP3. All of these examples use the lossy techniques. Okay. Um, Through the lossy compression technique, the goal is to remove only slight details or information that uh, they think that it's irrelevant to the human sensory experience. Okay, and at moderate compression level, it will not visually or virtually detectable by us lah. Okay. And so as for the summary, the lossless will preserve the data but has limited compression potential. But using a lossy, it will accept losses in exchange for the smaller file size. Okay. The choices depends on the usage context and the requirement of your application. Next, we have the history of the data compression. Okay. The development of the data compression techniques began in 1940s, late 1940s, with Shannon funnel coding and early variable length encoding methods. And in 1950, okay, the David Huffman, okay, developed a popular Huffman coding techniques uh, where it's assigned shorter code words to more frequent symbol, which enable an effective compression. And in last in last 15 years, arithmetic coding has largely replaced Huffman coding as preferred approach. Uh, Arithmetic coding looks at the entire message rather than the individual symbol. Okay. So Huffman coding was one of the early breakthrough in lossless data compression. It works by assigning variable length codes to input symbol with shorter codes for more common symbol, which will reduce the redundancy in symbol coding. Okay. Uh, so it shown that Huffman coding is the most efficient compression method using the fixed length code for symbol. So it came very close to the theoretical entropy limit. And then in the last 15 years, however, Huffman coding has been largely uh, replaced by the arithmetic coding, where it takes different approach than Huffman coding by rather than replacing each input symbol with a specific code word, it encodes the entire stream of symbol into a signal floating point number. Okay. Here, more bits are required in this output number to represent longer or more complex input messages. But arithmetic coding can compress data even more tightly than Huffman coding by looking symbol probabilities over the entire message. So, what we can say here, while Huffman coding was um, significant historically, now arithmetic coding was what replaced, and the performance is slightly has become the standard for entropy encoding in modern compression uh, scheme. Okay. Next, let's see the terminology that we'll use in multimedia data. We have a compressor and decompressor, which refer to the software and hardware that handles compression and decompression. While a codec is a device or program that compress or decompress data, and algorithm is the logic or the actual logic that govern the process of compression and decompression. Okay. Compression now is measured using the ratio, the compression ratio, original size ratioed by the compressed size. Okay. For example, if an image is compressed from 10 megabit down to 2 megabit, the compression ratio we can call it is 10 to 2, or if we divide by 2, it will become 5 to 1. Okay. The higher ratios indicate more effective compression. Right. Let's see the example of the Okay, the word analysis. Okay, word frequency analysis. Okay, it says that one swallow does not make a summer, neither does one fine day. Similarly, one day or brief time of happiness does not make a person entirely happy. Okay, first of all, what is the meaning of this sentence? Okay, um, it's mean that one positive experience actually not determine the whole situation or uh, lasting the happiness, right? So one swallow does not make a summer. Uh, when you say one swallow bird, does not mean the summer has arrived. Okay, so you should see or find more evidence uh, to describe or to say it's already summer. Okay. Similarly, it say that one good day does not guarantee a happy summer. Okay. Um. So the overall message is we should not put too much significance or on isolated uh, occurrence or short positive moment. Okay. Um, so you need to evaluate based on the uh, what to look more detail rather than look in a short period or limited information. Okay. All right. Okay. Get back to the word frequency analysis. Okay. So you can do a word count. For example, from words document, you can go to the review tab, click word count to see the statistic, including the word characters, paragraph, and page counts. Okay. Um, First, we know that okay from the previous slide, the character count in the sentence contain 148 characters, including the spaces and punctuation. Okay, and if we see one by one, okay, the analyze of the word frequencies. The word one occurs two times, day three times, does two times, not two times, and make two times. Okay. So we can see that a certain words like one, day, does are repeated and make up a high proportion of the sentences. Okay. Um, So we can say that for this sentence, character counts reveal the overall size, while word frequencies, okay, help to spot repetitive pattern suitable for the compression. Okay. Okay. We can how can we compress this sentence by substitute a numeric index for the most common words. We were able to reduce the storage space needed down to 139 bits, okay, from 148 bits, right? For instance, word one occur twice, okay, we can replace with the index one. Okay, let's see. Right. So by substitute the index for the most common words, it reduced the storage space needed from 148 to 139. Okay. And we can see the words pattern also stand out more clearly this way. So this is the example on how uh, the indexing technique, okay, can compress the data and reveal the interesting statistical properties without losing information. These same principles are used in the advanced compression algorithm. So we will have 1 swallow, 2, 3, 4, a summer. Okay. Neither 2, 1, fine. 5, similarly, 1, 5, or brief time of happiness, 2, 3, 4, a person entirely happy. Okay, walaupun kita tak nampak apa maknanya, tapi for compression data, it will give a significant effect. Okay, next is to look at the lossless compression algorithm. Okay, this will include the repetitive sequence separation, run length encoding or RLE, the entropy encoding, a Shannon funnel coding, and a Huffman coding. Okay, and remember the lossless technique allowed the original data to be perfectly reconstructed. Okay. First, to see at the repetitive sequence separation, where the data compression technique works by identifying and eliminates repetitive sequence of data elements in order to reduce the overall size data. So it look for repeating pattern that occur within the file. For example, you have a long sequence of identical pixel values in an image or the repetitive text in a document. Okay, when the repetitive sequences are found, they will be replaced with a shorter symbol or symbolic reference to single copy of the sequence. This techniques is utilized in many common compression format. For example, a video codec is used to detect and remove redundant frames or static backgrounds. JPEG compression is to use to suppress repetitive patterns in image data. And we have MP3 to eliminate repetitive audio segment, and gzip, which can replace a common text sequence that appear multiple times. Okay, so by identifying the repetitive sequence and reducing them to compact reference is a key technique to remove a statistical redundancy and compress a wide range of multimedia and documents data type. Okay, let's see the example of the repetitive sequence separation. We have a sequence of 894 and 0000000, and we can clearly identify a long repetitive sequence of 0 starting after 4. Okay, and to compress this, we need to define a flag or any symbol to represent that repetitive sequence. Here we will use F as the flag. You can use any other symbol or um, letter. Okay, bukan saja F, you can use A, B, C, and so on. Okay, so next we replace the long string of zero with a flag F. Okay, the number 32 is indicate the flag represent 32 zeros. Okay, so the compression or the compressed version will become 894F30 through F32. Okay, where 894 is the original starting sequence, F is the flag, denotes the repetitive zeros, and lastly 32 specifies the length of the zero sequence. Okay, so this will compress the data from 60 characters to just 6 compressed characters, and it is a substantial reduction in size. Okay, So what I can tell here is by detecting and symbolically represent the repetitive zero values, we are able to shrink the data while still allowing a full reconstruction of the original. Okay, this I think demonstrate the power of separation repetitive sequence for the compression technique. Okay. Next is the RLE, the run length encoding. It's another technique that replaces runs or sequence of repeated character with count and the symbol. And it is simple to implement, but the ratio depends heavily on the data content. For example, you have the character runs of 15 A's, okay, which normally would require 15 bytes to store, and with the use of the RLE, we would only require 2 bytes to store. Okay, count 15 is stored as the first byte and the symbol A as the second byte. Okay, sekarang kita akan ada 15 A. Okay, instead of write 15 times of A. Okay. Another example of the RLE is okay. Please look at this 16 characters string. Okay. Sorry, 000 P X X X X and A. Okay, so we can see it contains some repetitive character sequence. We have 306 lowercase of P's, 4 uppercase of X, and 3 lowercase of A. Okay, using the RLE, we can compress the string into 3 in bracket 0, 6 in bracket P, 4 in bracket capital X, and 3 in bracket A. So where the numbers represent the count for each character run. Okay, and from here we can see the by using the RLE encoded, it only requires 8 bytes to store, whereas the original uncompressed string need 16 bytes. Okay, so by applying this RLE, allow it to be represent in half of the space, which give you the ratio of 2 to 1. Okay, so but this case show RLE significantly reduce the size. Okay. Next, to see the another example, we have this sequence of 145, 145, 145. We can see that the repetitive of the pattern of 145 occurs 3 times in the sequence. So you can write 3 in bracket 145, where 3 is indicates the pattern repeats 3 times, and it reduces the original numbers uh, from 9 to just 4 numbers in the encoded form. Okay, and it will give the ratio of approximately 2 to 1. Okay, so I think this example illustrate how RLE can exploit the repetitive sequences in numeric data to achieve the lossless compression. Okay. Example 4. Okay. Example 4 is um to see how the incremental patterns in data can be leveraged or can be compressed to achieve the compression through the differencing. We can see the sequence of 1, 2, 3, 5, 6, 7, and 9. Uh, and these are the incremental value which each item increase slightly from the previous one. Okay, we can exploit by taking the difference between the adjacent values. For example, 2 minus 1 is 1, 3 minus 2 is 1 again, 5 minus 3 is 2, and so on. Okay, and it will gives a pair us a new sequence. Okay, which is 1, 1, 2, 1, 1, and 2. And this result has more redundancy and structure that can be further compressed. Okay, where we have 2 times of 1 and 2 times of 1. Okay, so the repeated sequence of 2, 1, 1, 2. Okay, so I think you can see this technique used in many algorithms to compress structured data like audio signal, time series, and many more. Okay, we can say that differencing is uh, simple, but it's a powerful concept. Okay, all right. So next to see the RLE in ASCII. Okay, ASCII, we know that it stands for American Standard Code for Information Interchange. It is a character encoding standard used for representing a text. Okay, ASCII text files contain the alphanumeric characters like letters, numbers, punctuation, marks, and symbol. And each character is encoded using 8 bits. This allow for 256 characters. Okay, using RLE is generally not effective compression for text file. Even in fact, it's by using RLE on ASCII text normally makes file larger rather than a smaller. Okay, that's there are several reasons why RLE does not work well for general ASCII data. Um, First is because it bloats file size with no added information, since the count values and the symbol will waste the space. The RLE encoded ASCII is less compressible by other algorithms since it breaks up the redundancy, and it indicates the text has poor information or it's messy with the character sequences. Okay. What else? Visually, okay, RLE encoded ASCII is lacks in aesthetics, or we can see it's not very pleasing. Okay, so can say that in ASCII text, RLE not give so many advantages. Okay, uh, we can use other method for compress the ASCII text. Okay, let's see the example of RLE in ASCII. For example, we have the quick brown fox jumps over the lazy dogs. Okay, by using the RLE encoded, we can have the 1T, 1H, 1E, 1Q, 1U, and blah, 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 blah. And because this example contains mix of letters, spaces, and punctuation, uh, it is a very high entropy set of ASCII symbol. Okay, if we try to apply RLE, we will not what we will just increase the length instead of compress it. So in this case, using or implement the RLE did not compress it at all. It's even make the version longer than the original raw text. Okay. So for the exercise here, do a RLE encoding for the following sequence grayscale value. You need to explain what is your encoding strategy and compute the compression rate. For example, you have 240 count how many consecutive consecutive values of 240. Let's see, we have 1, 2, 3, 4, 5, 6, 7. 7 times of 240. Okay, so you can write in bracket 240 comma 7 and so on. Okay. um Next, you need to count how many 238, how many 230, 229, 228, and 227. And next, to calculate the calculate the compression rate using the formula of compression rate is equal to original size divided by compressed data, or original size what two original original size divided by compressed size, or compression's rate is also equal to compressed size divided by original size. Okay, so you can try to answer this exercise. And all right. Okay, next, to go to the entropic encoding. Entropy assign shorter codes to more frequent symbol, which enable the data to be represented more efficiently. This approach gets us close to theoretical minimum number of bits needed on average per symbol, as defined by the Shannon entropy. Okay. For example, you have suppose we have a message that contain only two possible symbol, which is 0 and 1, and symbol 0 with the probability of 0.9, and 1 occurs with probability of 0.1. Then we can calculate the entropy, which is symbol by H, using this equation. So minus P0 log 2 P0 plus the probability of 1 log 2 P1. Okay, so we will have the answer of 0.469 bits per symbol. Okay, which means that on average we need at least 4.0 sorry, we need at least 0.469 bits to encode it in symbol in the optimal way. Okay, but no encoding can compress the message to less than 0.469 bits on average, but we can get close by assigning 0 to 0 for 1 bit and 1 to 111, which is 3 bits, which produce the average of 1.33 bits per symbol. Okay, so it is close to 0.469 limit. Okay, and so for the summary, it shows that how entropy sets a lower bound on the best compression achievable, and entropy encoding approach that theoretical limits. Okay, so this is what entropy encoding what make to us. okay, give us reduced bit requirement, shorter codes for frequent symbol, longer code for infrequent symbol, save storage space, and of course, it is the efficient compression. Okay. So this is the Shannon entropy. Okay, we use this equation like I uh, show previously. Okay. Um, so high entropy. Okay, kalau H2 tinggi, it will indicate the high disorder or unpredictability in the source, while low entropy suggests a more predictable or ordered information source. Okay, let's see or imagine or a pixel with 256 tiny dots or pixels, and each pixel has its own special colors. Okay, and no two dots have a same color. Okay, now if you count how often each color appears, you will find that each color shows up just once because there's only one dot with that color. Okay, you can use by using the entropy Shannon equation. Okay, uh, it will goes like entropy or H is equal to minus 1 over 256 times by log 2 256, where 1 over 256 is represent the chance of finding each color in the picture. Okay, and then the log part is a way to crunch the numbers and figure out the amount of surprise of or uncertainty. And at the end, this equation help us to measure how much information we get from this picture based on the different colors. Okay, and from the calculation, we will get the average number of bits needed to encode each color is 8. Okay. All right, so we have another example before I stop. Okay, for the next slide. Okay, what is the minimum average number of bit used to encode each color in this file? So by using the entropy method, you can show how it will goes. Okay, so 100 over 256 log 2 of 256 over 100. So this is for black. Next is for white. Also, the frequency is 100. Yellow 20, and red is 5. Sorry. Red also 5. Purple is 3. Blue 20, and green is 3 over 256. So by calculate this, you will get the entropy is about 2.0 006. Okay. So let's take a break, and I will continue in the next session. Thank you very much.